Today we're going to be talking about measuring center and spread, 5-number summaries, and box plots. When we talk about the center in statistics, we are talking about the mean, the median, or the mode. In this course, we're going to be focusing especially on the mean and the median. So the mean of a data set is the strict mathematical average. You've seen this many times. You take the sum of all the observations and you divide by the number of observations in the data set. So in statistics, the sample mean is represented by x bar, this x with a line on top of it. And next week, you're going to get a formula sheet that shows you this formula in notation that you may not be familiar with. It's going to look like this. And what this says is that x bar, the mean, is the sum. This sigma is a Greek letter. It means the sum of all the observations. X sub I means all of the observations, divided by the number of observations in the data set. So very quickly, this is how you calculate the mean. You add up all the numbers in the data set and you divide by the number of observations. So the average here is 8. And what this means is, let's say that these numbers 3, 7, 8, 10, and 12 represented the number of first cousins that people in 5th period statistics had, right? This means that if everybody had the same number of cousins, they would each have 8 cousins. For this reason, we call the mean the balance point of a distribution. So now let's say we change the number of cousins to be 3, 7, 8, 10, and 92 instead of 12. And we take the average of those and look at how drastically different the average is when we change this 12 to a 92. So because the mean is very sensitive to really big or really small numbers, we say that it's not a resistant measure of center. So what that means is that it's really sensitive to the influence of extreme observations. If you put in really big numbers or really small numbers and then you calculate the mean, it's going to be pulled very heavily in the direction of those numbers. In this case, we put in a big number relative to the other numbers at 92, and so that pulled the mean up substantially. Another measure of center is the median. You've also seen this quite a bit before. The median is the midpoint of a distribution. So the way that we find the median is we put all of our observations in order, so 3, 7, 8, 10, and 12, that same data set, and we cross off numbers from the largest end and the smallest end until we find the center number. So in this case, the median was 8. So now, let's look at what happens if we change that 12 to a 92, the same way we did when we calculated the mean. Okay, my median is still 8. So the median is not impacted by that big number the same way that the mean was. And for this reason, we call the median a resistant measure of center. It is not sensitive to the influence of extreme observation. So even if that number, that 92, were changed to a 10,000, right, the median of this data set would still be 8. Okay, so that's how we've taken the median when we've had an odd number of data values. What about when we have an even number? So same way as we started before, we're going to start crossing out values until we find our middle number. But here we don't have a middle number. We're looking for the number that's right in between 7 and 8. So to do that, I'm just going to average those two numbers that I'm left with, and my median is 7.5. So we've been set up pretty nicely to calculate our mean and median because we've been given a list of numbers. Now let's say we're doing this from a stem plot. Okay, so one way to calculate the mean and median from a stem plot is just to list out all the observations from the stem plot. Right? We have 0, 5 is my first observation, 1, 0. My second observation, 1, 0 is my third observation, all the way down. And I can capture them in a big list, and then I can calculate the mean. Mean is 31.25. I see in context here that we are talking about travel time for New Yorkers to travel to work. So I can say that the average travel time for a New York worker to get to work is 31.25 minutes. That's pretty easy, right? I can also calculate the median pretty easily off of this list of numbers by crossing out. I average my middle two values and I end up with a median of 22.5 minutes. Now, if you were taking the AP exam, when you take the AP exam, you're not going to have time to list out all these data values. It's a very time-tight test. So what we can do is we can actually find the median from this stem plot by crossing out the values the same way that we did here. So notice the first thing we did was cross out the smallest and the largest value. So I'm going to do that here. I'm going to cross out the smallest value and the largest value. Then I'm going to cross out the next smallest value and the next largest value. Notice I'm going from opposite ends. I'm going from smallest, crossing off smallest this way and largest this way. So I keep going and I end up with my two middle numbers. These stems and leaves represent 20 and 25. It's the same thing that I had here. So I can calculate the median to be 22.5 minutes. The median travel time for a New York worker to get to work is not 31.25 minutes, it's 22.5 minutes. On the AP exam, you are going to be asked to make conclusions about the mean and median given different types of data sets. So if you have a data set that is perfectly symmetrical or a real-world data set that's approximately symmetrical, the mean and median are the same. They are right in the middle of the distribution. Now, when we talk about skewed distributions, the mean is always going to be farther out on the tail than the median is, right? So notice in this left skewed distribution, my mean is farther towards the tail, and in this right skewed distribution, my mean is farther towards the tail. And the reason for that is because the mean is not a resistant measure of spread. It's going to be pulled towards those really small or those really large values, whereas the median is not. The median is just the midpoint, and it is a resistant measure of spread, so it's not going to be pulled. Here are some histograms that are also skewed. We sometimes talk about positive and negative skew instead of right and left skew. And if we were asked to calculate or identify roughly where the mean and median are, we can use the same strategy that we used up here. So in this graph that is right skewed, right? I know my median is going to be somewhere in here, it's the midpoint, and my mean is going to be further out along the tail. So we can sort of sketch what the distribution would look like, the curve on top of it, on top of our histogram, and then that allows us to identify roughly mean pulled towards the tail, median roughly the midpoint, and of course in a normal or symmetric distribution they are in the same place. So you will be asked at times to compare distributions and compare the center of distributions, and if the data are roughly symmetric, you're going to want to use the mean as a measure of center. It's a resistant measure of center, and it gives you a good idea of the average. So we use the mean if the data are roughly symmetric. And if the data are skewed, we're going to use the median to measure center because that median is going to be resistant to any extreme observations. So go ahead and pause the video and try the Check Your Understanding questions on page 53 in your notebook. So we've gotten a good idea about the center of a distribution. Now we're going to talk about the spread of the distribution. So one way to measure the spread of the distribution is to calculate the range of the data. So let's say we have a data set whose values go from 5 all the way up to 15. In order to find the range, we just subtract the largest value. We take the largest value and we subtract the smallest value. So the range of this data set from 5 to 15 is 10. The range is always listed as a single number. It's not listed as the two numbers here. So we say the data vary from 5 to 15, but the range of this data set is 10. Now, if we made that 15 239 instead, we made it some really big value, the range gets much bigger. The range becomes 234. So because the range is heavily impacted by very large or very small values, we'd say the range is not a resistant measure of spread. Okay, so the larger the range, the more variability in the data set, right? And the smaller the range, the less variability in the data set. Another way to measure spread is what's called the interquartile range. So the interquartile range is a better measure of spread than the range because it is less susceptible to being influenced by really big or really small observations. So here's the idea, is essentially we're breaking up our data into quartiles. And the way we're going to do this is we're going to count up the ordered list of observations starting from the minimum. That's what we've done here. Here we have a data set with the amount of fat in 9 McDonald's fish and chicken sandwiches. And the first thing we're going to do is we're going to locate the median, right? When we find the median, we know that half of our data lies above that value and half of our data lies below that value. The first quartile lies 1/4 of the way up the list. So to identify the first quartile, we are going to find the median of the data to the left of the median, right? So we crossed out our values until we could find this median of the left side. And that value represents a location that is 25% up the list, right? This value 15 is 25% of the way through this data set. We have our median, which is the 50% mark, it's halfway up the list. And then to calculate the third quartile, or the 75% location, right, we do the same thing. We find the median of the observations to the right of the median. The IQR, or the interquartile range, is the difference between Q3 and Q1, the third quartile and the first quartile. So to find that, we just subtract those data values, right? And this number, 9.5 grams, mean that the middle 50% of the data is between 15 and 24.5. In this context, the range of the middle 50% of the amount of fat in the McDonald's fish and chicken sandwiches is 9.5 grams. So we just calculated the IQR for this data set right here. Now, let's say we change the data set and we change this 9 grams to a 0 and this 33 grams to a 50, right? We made these values quite a bit larger and quite a bit smaller. However, if we calculated the IQR, it is exactly the same because the IQR is a resistant measure of spread. And the reason that the IQR is a resistant measure of spread is because it ignores the largest and smallest 25% of values, right? So this 0 and 50 have no bearing on our IQR because they are outside of the middle 50% of the data. So no matter how big or how small those values get, it does not impact our IQR. Another piece of spread is talking about outliers. So an observation is an outlier if it falls more than 1.5 times the IQR above the third quartile or below the first quartile. So let's look at grams of fat in McDonald's beef sandwiches. Here's the distribution, right? So we locate Q1, Q3, and the median using the tools that we just did. And the way that we calculate an outlier is by following the process listed here. So we find the IQR. Right, 29 minus 19, my IQR is 10. I do 1.5 times the IQR. That's the general rule of thumb for outliers. So any value that is 15 above my third quartile is an outlier. So any value greater than 44 is an outlier. And any value that is 15 below my third quartile is an outlier. So 19 minus 15 is 4. So any value less than 4 is an outlier. We're going to use all of these pieces in our next video to create what's called the 5-number summary and to construct box plots.